Hello students, welcome to the lecture on the exploration of oil, and after this lecture we will be able to learn the following objectives. Describe how carbonates reformed and trapped below the surface of the earth, explain hydrocarbon exploration, discuss on enhanced oil recovery methods, explain primary production methods. Let's start with the concept of the exploration of oil. Exploration is the process of trying to find accumulations of oil and natural gas trapped under the Earth's surface. Production is the process of recovering those hidden resources for processing, marketing and use. To understand the challenges the oil and natural gas industry faces in exploration and production, it helps to understand how oil and gas accumulations, often called reservoirs. Oil and natural gas are formed when decaying plants and microorganisms are trapped in layers of sediment and over the course of millions of years become buried deep within the earth, where underground heat and pressure turn them into useful hydrocarbons such as oil and natural gas. Exploration started in 1899 with the first recorded well drilled close to Brunei town, now known as Bandar Seri Begawan. Enthusiasm was high and 6 companies were involved in the oil search, including Royal Dutch Shell, which started operations in 1930 after discovering the Miri field in Sarawak, Malaysia. By 1918, all other companies had pulled out except Royal Dutch Shell, which continued to search and found some accumulation of oil and gas in Labi, Bilate in 1924. For a long time, this onshore Syria oil field was Brunei Darussalam's only producing field, despite some 48 exploration wells being drilled between 1914 and 1960. It was developed further in 1940 and production had risen to 17,000 barrels per day. Despite extensive damage to the field caused in World War II, post-war production peaked to 15,000 barrels per day. The breakthrough came in the 1960s when technological advances made offshore exploration feasible, and the Southwest Amper field was discovered in 1963, 13 kilometers off Kola Bilate. It was the discovery of the Southwest Amper gas field which sparked plans for the Brunei LNG plant project. The Brunei LNG plant began its operation in 1972 as one of the world's first large-scale liquefied natural gas LNG plant on the coast of Brunei Darussalam, setting new standards in engineering technology. Brunei LNG proved that large quantities of gas could be liquefied safely and shipped over long distances, becoming a model for similar ventures throughout the world. The layers of rock in which hydrocarbons are formed are called source rocks. High pressures underground tend to squeeze hydrocarbons out of source rocks into what are called reservoir rocks. These are rocks such as sandstone, which feature pores large enough to permit fluids like oil, natural gas and water to pass through them. Since oil and natural gas are less dense than water, they will float upward toward the surface. If nothing stops this migration, the oil and natural gas may reach daylight through what is called a surface seep. More often, however, hydrocarbons' path upward is blocked by a layer of impermeable rock such as shale or by some other geological formation. These trap the oil and natural gas either in an underground pocket or in a layer of reservoir rock so that it may be recovered only by drilling a well. There is not any way to be absolutely sure where new oil and natural gas reserves are located, so petroleum engineers need to collect clues as to what lies deep beneath the Earth's surface. Advanced technology has revolutionized the exploration process for oil and natural gas and helps them pinpoint potential reserves with greatly improved accuracy. Let us now discuss the hydrocarbons reformed and trapped below the surface of the earth. Petroleum refers to any naturally occurring hydrocarbons that are found beneath the surface of the earth, no matter whether these hydrocarbons are solid, liquid or gas. The solid and semi-solid forms of petroleum are called asphalt and tar, whereas liquid petroleum is called crude oil. And of course, there is natural gas which can be associated with oil or found entirely by it. Mankind has used the various forms of petroleum for centuries. The Babylonians used asphalt to pave paths and caulk boats, and the ancient Egyptians used tar to prepare their mummies. In fact, mummy is a derivation of the Arabic word for tar. Condensate was an essential ingredient of Greek fire, the secret weapon of Byzantium, and the ancient Chinese used natural gas to light their imperial palaces. Oil and gas traps. All oil and gas deposits are found in structural or stratigraphic traps. We have heard that oil is found underground in pools, lakes or rivers. Maybe someone told us there was a sea or ocean of oil underground. This is all completely wrong. Most and gas deposits are found in sandstones and coarse grained limestones of oil. A piece of sandstone or limestone is very much like a hard sponge, full of holes but not compressible. These holes or pores can contain water or oil or gas, and therefore will be saturated with one of the three. The holes are much tinier than sponge holes, but they are still holes and they are called porosity. The oil and gas become trapped in these holes, stays there for millions of years until petroleum geologists come to find it and extract it. When we hold a piece of sandstone containing oil in hand, the rock may look and smell oily, but the oil usually will not run out, cannot squeeze sandstone like a sponge. The oil is trapped inside the rock's porosity. Oil formation and oil movement. The very fine-grained shale we talked about is one of the most common sedimentary rocks on earth. In many places, thousands upon thousands of feet of shale are stacked up deep underground. It is not unusual to have layers in the earth's crust made up mostly of shale that are 4 miles thick. These shales were deposited in quiet ocean waters over millions of years' time. The tiny, gigantic kingdom. In the deep ocean, far from land, about the only sediment deposited is the fine-grained clastic rock known as shale. But what about the oil and gas? For the answer, we need to move to the ancient oceans that once covered almost all of the earth. A lot of other material is deposited along with the clay or mud-sized sediments. We often think of sharks and whales as being the kings of the deep oceans. Actually, there are other animals that have established giant kingdoms in the sea, the largest and most impressive kingdoms of all. These animals are the various kinds of microscopic creatures, both plant and animal. Most of them would fit on the head of a pin. They are tiny, but there are uncountable trillions of them. But these creatures die, they sink to the bottom and become part of the sediments there and will eventually turn into shale. The animals die by the trillions and rain down on the ocean floor all the time. And since the beginning of life on earth, they have been living their exciting lives in the ocean, dying, sinking to the bottom and becoming part of the ocean living matter that is part of most shale rocks. It is the trillions of tiny animals that make up most of the junk, and the scientific name for this junk is ooze, deposited on the ocean floor. It is a very fine-grained group containing a lot of organic material mixed with the clay-sized particles that form shale. It is a very fine-grained group containing a lot of organic material mixed with the clay-sized particles that form shale. It is called organic rich shale. Later, when thousands of feet of organic rich shales have piled up over millions of years and the dead animal bodies are buried very deep, more than 2 miles down, an amazing thing happens. The heat from deep inside the earth cooks the animals turning their bodies into what we call hydrocarbons, oil and natural gas. At first, the oil and gas only exist between the shale particles as extremely tiny blobs left over from the decay of the tiny animals. Then, the crude oil samples intense pressure of the earth squeezes the oil and gas. Then, the crude oil samples intense pressure of the earth squeezes the oil and gas out of the shale, and the oil and gas fluids together in a porous layer and move sideways many miles. On their way, they may meet up with other traveling oil or gas fluids. Types of trap. There are two types of traps. These are structural traps, stratigraphic traps, structural traps. These traps hold oil and gas because the earth has been bent and deformed in some way. Stratigraphic traps. Stratigraphic traps are depositional in nature. This means they are formed in place, often by a body of porous sandstone or limestone becoming enclosed in shale. The shale keeps the oil and gas from stratigraphic trap escaping the trap, as it is generally very difficult for fluids, either oil or gas, to migrate through shales. In a sense, this kind of stratigraphic trap is surrounded by cap rock. Petroleum geology. Several geological elements are necessary for oil and gas to accumulate in sufficient quantities to create a pool large enough to be worth producing. These elements include an organic rich source, rock to generate the oil or gas, a porous reservoir rock to store the petroleum in, and some sort of trap to prevent the oil and gas from leaking away. Traps generally exist in predictable places, such as at the tops of anticlines, next to faults, in the up-dip pitch-outs of sandstone beds, or beneath unconformities. To find a convergence in the subsurface of the geological elements necessary to form an oil or gas pool requires a careful blend of science and art. The collection of seismic data involves sending shock waves into the ground and measuring how long it takes for the surface rocks to reflect these waves back to the surface. The shock waves that are used today are usually generated by pounding the earth with giant vibrator trucks, but in the past, geophysicists preferred to explode small dynamite charges in shallow holes. Geological and geophysical clues are enticing, but drilling is the only way to learn if an oil or gas field really exists. Once a well is drilled, well logs yield data on the types of rock present and, most important, what fluids these rocks contain. The information interpreted from the logs is used to decision whether a well should be completed or used to produce oil and gas, or filled with cement and abandoned. The logs are also used to update the geological models originally used to locate the well. Today, the average wildcat well has only one chance in 10 of finding an economic accumulation of hydrocarbons. A rank wildcat, if drilled in a frontier area, stands only one chance in 40 of success. Drilling. The only way to find out if a trap contains oil or gas is to drill into it with a well. In the early days, wells were drilled with cable tools in which a heavy drill bit on a cable was repeatedly dropped up and down on the ground to literally chop a hole down to the trap. Today, we use rotatory drilling, in which a bit on the end of a length or of drill pipe is rotated. A mixture of water and mud called drilling fluid is pumped down the pipe to flow through the bit, creating a drill site. Drilling for oil and natural gas is a complex process, but advanced technology has made the job more efficient and productive while providing less impact on the environment. Some important points in creating a drill site are: some people believe that oil and natural gas companies can explore for oil wherever they want. This is not true. Companies must secure permission from the owner of the mineral rights, whether the owner is a private citizen or the government. The drilling derrick is used to position and support the drill string. Modern drilling equipment comes in a wide range of sizes. Many wells can be drilled with equipment that requires far less space than in the past. Drill rigs now run on electricity to supply the power to turn the bit and raise and lower the drill pipe and casing. Since most drilling occurs in remote areas, the electricity is supplied by electric power generators that run on diesel fuel. These generators make drilling rigs much quieter than in the past. The drill bit uses 3 conical shaped cutting surfaces to grind rock into rice-sized particles. The newest bits drill 150 to 200% faster than similar bits just a few years ago. The drill string consists of lengths of pipe fastened to each other and to drill the bit. The drill string transmits power from the top drive to the drill bit. As the drill cuts into the rock, drilling mud is added to the hole. This helps cool the drill bit, and the mud is circulated to bring cuttings to the surface. The weight of the drilling mud keeps the hole open. It also helps counteract the pressure of any gas or fluids encountered along the way, in this way preventing a well from loss of control or blowout. Now moving on to the next topic, we will study the hydrocarbon exploration. A look at the exploration history of the important oil areas of the world proves conclusively that oil and gas seeps gave the first clues to most oil-producing regions. Many great oil fields are the direct result of seepage drilling. We usually find oil in new places with old ideas. Sometimes also we find oil in an old place with a new idea, but we seldom find much oil in an old place with an old idea. Natural petroleum and gas seepage is an indicator of accumulations, migration pathways, or mature source kitchens. Historically, onshore seepage mapping has proved valuable in many parts of the world, including North America, the Middle East, Iran and Iraq, and Indonesia. Seepage mapping is much more difficult offshore but has been documented in the North Sea, Bass Strait, and the Gulf of Mexico. Hydrocarbon exploration considerations. Exploring for hydrocarbons is a risky and costly business, but the rewards can be large. Important factor to consider includes developing a gas field is much harder than an oil field. A market for the gas must be found and a lot of production, processing plant and pipelines must be installed. What is the water depth for offshore exploration? Drilling and producing oil in 100-meter water depth or less is relatively easy, but the easy acreage has usually been explored hard. Let's know the meaning of enhanced oil recovery methods. Enhanced oil recovery (EOR) is a term for special techniques to increase the amount of crude oil that can be extracted from a field over and above conventional primary depletion or basic water flooding, which typically will recover 20% to 40% of the stock tank oil initially in place. STOIP. Essentially, these can be determined in 4 basic methods. Chemical method. The chemical method includes the following. Polymer flooding. Polymer flooding is one of the most widely used EOR methods to retrieve oil left behind after conventional recovery processes. It is an augmented water flooding technique introduced in the 1960s, mainly used for heterogeneous reservoirs to retrieve oil after areas in the reservoir with high permeability have been highly water flooded.
During low-carbon power production at the HYDROCARBON plant, carbon dioxide, or CO2, is captured, compressed to a near liquid state, and transported via pipeline to the Oxy Elk Hills operation for enhanced oil recovery, or EOR, and sequestration. Extensive geological analysis has identified Oxy's Elk Hills field as one of the premier geologic traps in North America for enhanced oil recovery with permanent CO2 storage due to its unique shape and secure geology. Millions of years ago, oil began migrating to the Elk Hills Reservoir, where the tiny pore spaces within the dome-like structure of the sandstone formation have retained the oil in place. The oil and gases have been contained underground by a thick, impermeable layer of shale or caprock, hundreds of feet thick, that forms a barrier naturally preventing fluids and gases from rising to the surface. Enhanced oil recovery with permanent CO2 sequestration or storage is a process where CO2 is injected into deep reservoirs to improve oil production, and is a technique already used in more than 100 U.S. oil field operations. CO2 will be transported from HYDROCARBON to the Occidental Elk Hills operation, where enhanced oil recovery with permanent CO2 storage will be used to extend the life of Oxy's oil field. The CO2 is injected in a liquid-like state to a depth greater than 1 mile underground, the equivalent of 4 Empire State Buildings stacked one on top of the other. The CO2 travels down the wellbore to a precise and predetermined location within the rock formation that provides the greatest enhanced oil recovery and permanent CO2 storage benefit. As the CO2 mixes with the oil in the formation, the oil swells, reducing its viscosity, allowing the oil to flow more easily through the interconnected pore spaces towards the production well, which can result in 10 to 30% more oil production. During this process, the CO2 becomes trapped in the rock and is permanently stored in the pore spaces, in the same way oil was trapped in the formation millions of years ago, with the caprock serving as a physical barrier for the containment of the CO2. Other trapping mechanisms include the dissolution of CO2 in formation fluids and mineralization of the CO2 within the rock pore spaces. As fluids and gases are produced from the well, they flow through a series of vessels that separate them at Oxy's EOR plant. The oil is separated and stored in tanks prior to being delivered to the American market. A portion of the injected CO2 may be produced with the oil. This CO2 remains contained within the process system at all times and is immediately separated and combined with CO2 arriving from HYDROCARBON for re-injection into the formation. This is known as a closed-loop process and ensures the injected CO2 is ultimately retained within the reservoir. Several methods will be employed to monitor, measure, and verify the containment of the CO2 in the formation 24 hours a day, 7 days a week. Sophisticated detection techniques and equipment are used in the reservoir and on the surface to ensure the accurate and safe storage of the CO2, the protection of underground sources of drinking water, and the public. In addition, the containment of CO2 in the target formation is further verified by the monitoring of CO2 levels in a gas production reservoir above the injection zone. Successful carbon capture and enhanced oil recovery with permanent CO2 storage in a project of this magnitude requires extensive skills, resources, and experience.
Chemical flooding. In a chemical flood, chemicals are injected with a water flood to improve the displacement efficiency. A chemical solvent is specially developed for adaptation to the specific structural characteristics and physiochemical properties of a reservoir. Physical method. The physical method includes the following. Thermal recovery. Thermal methods raise the temperature of regions of reservoir to heat the crude oil in the formation and reduce its viscosity and or vaporize part of the oil and thereby decrease the mobility ratio. Thermal methods include the injection of hot water, steam or other gas, or by conducting combustion in situ of oil or gas. Gas drive oil. Gas injection or miscible flooding is a general term for injection processes that introduce miscible gases into the reservoir. A miscible displacement process maintains reservoir pressure and improves oil displacement because the interfacial tension between oil and water is reduced. This refers to removing the interface between the two interacting fluids. This allows for total displacement efficiency. Primary production methods. Primary production, as the term suggests, is the first method of oil from a well. When discovered, a crude oil reservoir contains a mixture of water, oil and gas in the small pore spaces in the reservoir rock. Initially, the reservoir holds these fluids under considerable pressure caused by hydrostatic pressure of the groundwater. At this pressure, a large part of the gas is dissolved in the oil. These two fluids, the initial water connate and the gas is in solution, combine to provide the driving force for moving the oil into the well. If the pressure on the fluid in the reservoir energy is great enough, the oil will flow into the well and up to the surface. In this case, no pumping equipment is required. If the reservoir energy is not sufficient to force the oil to the surface, then the well must be pumped. In either case, nothing is added to the reservoir to increase or maintain the reservoir energy, not to sweep the oil towards the well. The rate of production from a flowing well tends to decline as the natural reservoir energy is expanded. Water drive reservoirs. A water drive reservoir has a hydraulic connection between the reservoir and a porous, water saturated rock called an aquifer. Solution gas drive. Crude oil under high pressure may contain large amounts of dissolved gas. When the reservoir pressure is reduced as fluids are withdrawn, gas comes out of solution and displaces oil from the reservoir to the producing wells. The efficiency of solution gas drive depends on the amount of gas in solution, the rock and fluid properties, and the geological structure of the reservoir. Recoveries are low, on the order of 10 to 15% of the OOIP. Now in the end, let us summarize what we have learned in this lecture. Several geological elements are necessary for oil and gas to accumulate in sufficient quantities to create a pool large enough to be worth producing. The collection of seismic data involves sending shock waves into the ground and measuring how long it takes for the subsurface rocks to reflect these waves back to the surface. Protecting the aquifer from contamination is a major concern of the oil and natural gas industry. If the pressure on the fluid in the reservoir energy is great enough, the oil will flow into the well and up to the surface. A crude oil is undersaturated when it contains less gas than is required to saturate the oil at the pressure and temperature of the reservoir.